And next, we will have a panel discussion on the theory research in the big data and AI era. And today is our great honor to invite a few very outstanding theory researchers and opinion leaders to join the panel. I will briefly introduce them. And for the panelists, once I mention your name and introduce you, please kindly come up to the stage. We have already prepared everything for you. Our first panelist is Professor Xiaotie Deng. Xiaotie, yeah, please. Xiaotie is currently a chair professor at Peking University. He is an ACM fellow for his contribution to the interface of algorithms and game theory. And he is an HV fellow for his contribution to the computing in partial information and the interacting environment. He is also a member of Academia European. And our second panelist is Professor Pinyan Lu. Pinyan, due to the pandemic, Pinyan is online. You can see Pinyan on the screen. And Pinyan is currently a professor and the founding director of the Institute for Theoretical Computer Science at the Shanghai University of Finance and Economics. Pinyan is a recipient of the ICCM Silver Medal of Mathematics. He is a distinguished member of ACM and CCF. And our third panelist is Professor Liwei Wang. And Liwei is currently a professor and a vice dean of the Department of Machine Intelligence, Peking University. Please. He is well known for his outstanding research on machine learning theory, and he was also named among the AI AS10 to watch. And finally, we have our double Wei Chen, our two Dr. Wei Chen, the chair and the co-chair of our theory center. They will also join the panel. Okay, please sit down, and we will start our conversation. Okay. So right now, John has given us a very insightful keynote speech, and he talked a lot about what is the fundamental research, how to do good research in industry lab, and also how to improve the education in universities. And I think many of you in the audience may already heard that famous saying from Vapnik, nothing is more practical than a theory. So my first question to all the panelists is, would you please share with us your experience, especially in your domain, from which you think theory is truly important, and why it's especially important in this new big data AI era? I know some of the panelists have prepared some slides to assist your sharing. So let's start from Xiaotie.
In game theory, and at this time, I would say game theory in the digital reality. So my recent stream of my research area has started with incentive ratio in market equilibrium. This is a typical question in economics. Like in mechanism design, we are interested in design that people do things truthfully. But in market equilibrium, it has been known long time ago, since economists, they say this is it's not incentive compatible, it's not truthful. People may lie in market equilibrium settings. Our study started in this direction in understanding why the agent would lie in market equilibrium. It's already known by economists in the past, so our study focused on understanding it quantitatively. From economists, they find out people may not lie because there are so many people in the market, and the deviation by individuals may be when mixed up in the big economy, it disappears. But with information technology, this has been changed. And activities may be coordinated. In market equilibrium, there is a basic assumption is individual doesn't change their strategies. But in market equilibrium, in big environment with information aggregation, this is possible. So actually, our first work has been positive in that direction. We studied the BitTorrent mechanism. That is a mechanism in in distributed systems long time ago, like 18 years ago, and we find out it's truthful. So we justify its success like in terms of incentive ratio. It's like it's truthful. The algorithm is truthful. This is this is believed by people in the past. So we give a formal proof in that direction. In that, we starting with that direction, we try to understand learning and data privacy. Again, that is like we try to study Beijing auctions. We know MSR auction is one of those questions. And our first study tried to understand it in like a statistical learning approach. So we find out that people may be able to lie about their distribution. So lying about distribution can improve one person's strategy and can change their strategy, and they can gain a little bit. But that may cause other players to do the same thing. Eventually, we will reach a beating game equilibrium in the auction setting. When we try to learn players' distribution, and when we try to learn, then changes it changes the final equilibrium. That dynamics we believe has some effect on the sponsor search setting, and we had a clear analysis recently. So furthermore, we run into mechanism design issues in automated market design. And in 2008, we did something in that direction. We tried to design a prediction market for the Olympic game result. But eventually, our design didn't work well because agents, they may not do things they may not do things as we planned. And eventually, the economy, in the prediction market, the economy went bankrupt. Not bankrupt, actually, somebody take over to make all the prediction as dominate in the eventual design. So we find out it's a very difficult problem to do automated market design in the real, and that is happening currently in the blockchain economics designs. So that is also very important issue, I think, in terms of game theory in digital reality. So finally, we are entering into this age of metaverse. We expect this to happen. I think that's a good direction we would follow.
Thank you, Xiaotie. Yeah. Truly, I still remember many years ago, Xiaotie, we discussed how to really let machine learning meet game theory. Because game theory talk about the worst case analysis, and machine learning focus on the expected cases. And also the mechanism design, game theory are really important for many internet applications, especially when humans get involved, like auction design for ads and also metaverse you mentioned. So I think this is really a very important direction that maybe in the future our theory center should look into. Thank you very much. And next, Pinyan, I know you are also a game theory expert, right? So how about share your opinion along those lines?
Yeah, thanks. Yeah, thanks for inviting me, and it's really a pity that I cannot be there on site, and I would really like to come back to MSI. And congratulations to the Theory Center, and it seems that is all exciting thing like Theory Center and the Shanghai site happened when I left. So okay, today I would like to share some observation I recently find very interesting. as a computer scientist, like either selectation or non-selectation, we are design algorithm in our daily life. But I observe that the way we design algorithms are very different. Like in TCS, in selected computer science, we usually define the mathematical problem and fix the evaluation metric, which would be like the worst case running time or the approximate ratio or things like that. Then they are fixed forever. Then researchers are designed different algorithms to get better and better performance. Then if you can get a design algorithm which have the better performance than all the previous one, you can publish a paper. And usually the algorithms are very different and also very sophisticated. If the algorithm is very standard, usually you cannot really publish a paper. That's what we did in selected computer science. And the data or the problem instance are not really play any role in this process. We just define the mathematical problem and fix the evaluation matrix, and then we do design algorithm for that. But like in OR, in ML, or in industries, the things are really different. They are usually the algorithms are somewhat fixed. It should maybe some solver like ALP solver, MIP solver, SAS solver, or like redesign or things like that. The algorithms are somewhat fixed. Then you try to formulate a real problem in different way so that the algorithm, the given fixed algorithm can have a very good performance and the result is good in the final data. That's the way usually people design algorithms. Not design algorithms, actually you reformulate the problem and make use of the non-algorithm and get some result and evaluate the result in data. That's a really different way, and I think they both have advantage and disadvantage. So I really think that the way we should design algorithm should be kind of combine these two views, and it could be a co-evaluation about these four things: the problem definition, the algorithm design, the evaluation matrix, and also the data, which is the problem instance. Usually, first we based on the description of the problem, we can define the mathematical problem. What is the instance? What is the constraint? What is the object function? What is the solution we find? Then we may try to design some basic algorithm for that. Then after we run the algorithm on the data, we may see something which actually sometimes not only changes the algorithm, but also changes the definition of the problem, because that describes the constraints or the objectives of the problem, sometimes not sufficient. After you've seen the real instance of the problem, you will have get better feeling of what should be the real good definition of the problem and what should be the object function. After you change the object function, you may also change the algorithm, and it's kind of it's an interplay with this first thing, and finally we get some algorithm which is good in the real performance. That's the way we should do in design. I think in this we can really combine some selective some algorithm design approach or ideas from selective computer science, and also play with the real data and for the definition, and then we can get a better algorithm, not only the fixed algorithm as used in the industry or in machine learning or in OR. So also from this perspective, I also find that there's three really different algorithm design approach. One is a selective algorithm, which actually have a worst case guarantee, either in the terms of the running time or the ratio or things like that. Also, we have this heuristic algorithm. We have some meta heuristic like the many algorithms like the local search and also the grid design, things like that. They are actually quite powerful in the real application, but they don't have any selective guarantee, and sometimes it will fail visibly, and in some cases if the instance looks very different as before. So also recently there also are change in machine learning, trying to using machine learning to design algorithm for like combinatorial optimization or for constraint programming, things like that. Then the machine learning approach is really promising in the sense that it may look really have the feedback from the data, which is the problem instance, to the algorithm, because you can really learn some patterns from the instance, the particular instance, and which give feedback for the algorithm, the parameters or the design in the algorithm, which can get a better performance. So I think it would be very promising to combine all these approaches, like the selective algorithm, heuristic algorithm, and machine learning idea to get a very better algorithm in this big data area. Okay, I will stop here. Thank you.
Thank you very much, Pinyan. So as a theoretical computer scientist, you mentioned the co-evolution of the different algorithm design paradigm, like the theoretical approach, traditional theoretical paradigm, and also the machine learning paradigm. And I guess as a machine learning researcher, machine learning expert, Liwei must have more to say. So what is because we are mentioning the big data AI era, it is your era, right? So just share with us some of your thoughts.
So actually, it's very interesting to look at a history of the development of machine learning. I divided the history of machine learning into two parts. One is before deep learning, and the other is deep learning. So let's first look at what is the machine learning before deep learning. Actually, at that age, most of the practical algorithms are developed by theorists, like boosting, SVM, kernel methods, bagging, random forest. So let me just take boosting as an example. Boosting was developed in the late 90s, actually it's in 1990. Rob Shapiro developed the first boosting algorithm. But the problem they try to solve is a pure theoretical problem. It asks if weakly learnable is equivalent to strong learnable. It's a pure theoretical problem. It actually has nothing to do with practice. But for this very pure theoretical problem, they get the boosting algorithm. The first version of boosting algorithm is not practical at all. But then gradually, they improve the algorithm and make it practical. So now boosting is still a very important algorithm for machine learning. So for SVM, bagging, random forest, it's all the same. But now, in the deep learning era, say from 10 years ago, it's a totally different story. So deep learning is empirically very successful. But the algorithm and the model are mainly heuristic. There's some theoretical inspirations in deep learning, but mainly engineering techniques. So we see the neural network model, it's purely, and there's no theoretical understanding of why deep neural network works until now. So although it's very successful in practice, but there are also very important drawbacks. For example, the adversarial robustness is a major drawback of deep neural networks. So I think everybody heard of the adversarial robustness problem. And also the data efficiency, also the generalization and interpretability of deep neural network. I believe these problems of deep neural networks should be conquered from a theoretical way. And especially I think for adversarial robustness and out of distribution generalization, for these problems, we have a very strict mathematical requirement for the objective we want to achieve. And for these kind of problems, a theoretical approach is necessary. Okay.
Thank you, Liwei. You're very insightful. And then we will have our two colleagues in MSRA to share with us. I need to say a few words here, because when I initiated this theory center, I think about why we are powerful enough to make it a huge success. Eventually, I got a very good answer. You know, for other organizations, maybe they only have the linear power, but we have the quadratic power because we have two-way chain. And when I make the proposal, I write Wei Chen square. Right? This is a very powerful director and co-director of our theory center. So I think you must have a lot of plan in your mind about how to run the center and what are our major investment areas. So this is time for you to share with the audience. Yeah, please.
Thank you, Tian. So I'm going to first talk about mostly how the current research in optimization is driven from the traditional part of theoretical computer science. I think Wei will share later about her side, more on the machine learning side. So from the TCS side, optimization is always at the core. Right? From the very beginning, designing algorithm is to do something better, to do something faster, like optimization. And classical optimization is typically model-driven. You give all the model aspects that, and including all the parameters, then you try to do the best thing. For example, the famous Dijkstra's shortest path algorithm. You need to feed the algorithm with a complete graph, and every edge you need to feed the delay parameter of that edge. Then you just run the Dijkstra algorithm in near linear time, you can find the shortest path from A to B. Now, in big data era, these things are gradually changes, actually sometimes very fast, because people are looking to data, people making their decisions and optimization based on fast-growing data. Like, for example, in the shortest path, the delay parameters are not fixed right now. You have to constantly gather the information from the environment, if there is a road network or computer routing network, and that changed the game, because now data is part of your optimization. So this demands a new paradigm. We call it data-driven optimization. That means you need to do end-to-end from gathering data to processing data to do optimization. And fortunately, for data-driven optimization, of course, the first part people usually think is by machine learning. Starting from the data, how do you process data to learn a model, plug in some machine learning framework. Okay, that can be done. But that's not the end of story. Actually, in some recent research, we start to notice that there are new problems when you try to integrate machine learning with optimization. So I list a few areas here we want to further explore. For example, optimization from samples. There are recent research showing that just simply by doing machine learning to learn a model, then doing optimization, they have some drawbacks. In some cases, you cannot do end-to-end optimization. And how to circumvent this? This is something I and my colleagues and collaborators are working on this. And another area is when you have data, can we cleverly use feedback loop, not just one-way street, doing one-way direction from data to optimization. If your optimization result can give you feedback to further help you to do further better optimization, that is important. For example, in the routing network, again, if you can learn your routing result for the past time and then use those feedback to do better routing in the future, that is very important. And that leads to the current study we call combinatorial online learning. There are certain other areas like streaming algorithms to deal with uncertainties, is also dealing with the constant coming data. And reinforcement learning is a learning framework that also handle with data and how to do optimization. But the important thing is integration. So my last point is actually echoes what Pinyan said in some extent. Basically, optimization is from traditional TCS side, while learning have a new learning framework. How to integrate these two frameworks together? We think this is a challenge, but it's also opportunity to us because we have the expertise. We have collaborators, and in our lab, we have expertise on both sides. So I'll end for now. Thank you.
Okay, next. The next slides, please. Okay, thank you all for coming here. I think when I was a student, my advisor, Professor Ma, told me that we can do pure math or applied math. But if you choose to do applied math, then you need to look at the real problem. So I come to Microsoft. Okay, so in the past 10 years, we look at many applications for machine learning, like the recommendation and search. We provide the theoretical foundation for learning to rank. And we have also invented some solutions for how to accelerate the training of big deep neural network models. And now, as Liwei mentioned, that deep learning, to be honest, its foundation is not so solid as the shallow learning. So we are now facing the bottleneck of how to interpret the deep learning and how to make it to be trustworthy. So, so I think it is one of very important direction that need our collaboration to all the professors, all the researchers for the theoretical understanding for deep learning. And thank you. And when we looking forward, I think besides the deep learning theory, we need new machine learning theory. With the power of the deep learning, we are using it to solve not only the AI tasks like intelligent perception, but also to empower industry and science. And in this kind of domains, we have traditional domain knowledge, maybe characterized by math or theoretical computer science, like the dynamic systems and control theory for the continuous dynamic systems, and the operation research for resource optimization problem, and not mention the theoretical physics and biology and sustainability theory in that kind of science. So, I think most of us has already heard that AI even can help us discover new math. So I think the very crucial feature for the new machine learning theory is the intersection of the learning theory, the learnability theory, with the domain knowledge in the other direction of science. So I think I can stop here, and maybe we can discuss this later more.
Thank you, Wei. Yeah, I would like to thank both Wei Chen, and I always have a joke. So I look forward to see a paper co-authored by Wei Chen and Wei Chen, both from Microsoft Research Asia, to confuse the reviewers. Okay, thank you very much. And then that's the next round of our questions. Once again, we will first direct the question to Xiaotie. And Xiaotie, I know you're a very, very influential researcher in the theoretical computer science, with very widespread connections with people in Europe, US, and Asia. And especially in the field of algorithm game theory, you are one of the pioneers and founded the conference Wang. And I'm also very fortunate to chair the Wang 2014, probably, and under the leadership of Xiaotie at that time. And so my question is, in your view, how should we make stronger connections of the theory researchers worldwide and generate bigger impact? For example, through some new initiative, some new conference or other collaboration program. So any insights here?
Yeah, thank you. Yeah, actually with Professor John Hofkoff, we are developing a new conference called the International Conference on Theoretical Computer Science based in China, mainly based in China. We have had 2 conferences. Our goal is trying to make it a high-quality conference. We started with a new approach. We try to get Chinese scholars to speak, like a lot of invited talks. So our goal is like we get our young generations of scientists in theory to speak and to make their voice heard. And also, we in the first, fortunately, in the first conference, we had one undergraduate student speaker and from Peking University who won the best paper award in folk stock. So that was our luck. And subsequently, we find out a lot of young professors coming back from US in Chinese universities. So we made a rule. So every time we invite a speaker, basically we hope they are fresh speakers. They are not like spoken last time in our conference, but they may have done it in other places, but not in our conferences. So that gives everybody a case to speak what they do in theory. And this is one direction. Another direction, we also get some advice from great scientists in America and Europe. Like they kind of say, maybe you want to do something in your favor or in your perspective that will be done better in Asia, in China. So that is also something we try to move in a direction like in tracks. So we will focus on tracks so that the research area will be like something probably will do better, and there is a chance we can do better. So that is another approach we are trying to do. And last 2 times we were in Beijing University, so next time it will be in Hong Kong, and probably the year after will be in Macau, so we'll be moving around. Thank you, John. It's like really supported by John. Yeah.
Yeah, thank you very much, Xiaotie. I think the establishment of the MSR Theory Center will also be a kind of our commitment to the research community. Hopefully, we can join force in some events.
That would be great. Yeah, and also Microsoft, like one of the conferences which was very successful in Asia is SIGGRAPH Asia, which Microsoft also supported a lot. I talked to people organizing it. So hopefully this time we will have your support.
Yeah, we look forward to that.
Yeah.
Thank you very much, Xiaotie. And the next question goes to Pinyan online. So Pinyan, you in your open sharing, you already mentioned many different algorithm design paradigms. And we all know, Pinyan, you did really truly world-class research in the theory of complexity of accounting. And your research also expanded to many other domains like algorithm game theory, and recently also look into machine learning. So that's really kind of from hardcore TCS to many other different areas. So I am sure you have a lot to say along this direction and about your experiences. So this is another time for you to share with us.
Okay, thanks, T. Yeah, usually when I introduce what is selective computer science to people who is outside our community, I really emphasize the 2 points you just made. One is that TCS is just in the foundation of computer science and maybe in the whole information science. So it provides the foundation, the algorithm complexity, which is really important. And another point I would like to overemphasize that TCS is also in the frontier of the interface between computer science and other disciplinaries. That's because really TCS studies the algorithm and also have the idea of this computational thinking. And in many other areas, like in natural science, nature is governed by physical law, and this law can be viewed as some way as an algorithm or as an optimization. Also, the social behavior is governed by the incentive of the people, which is also kind of a algorithm thinking, which maximizes home utility. So with this observation, it's really very important to combine this algorithm thinking with this other disciplinary and have very fruitful outputs. And especially become when the system become more and more complicated, like in natural science or in social science. When the system become more complicated and the computer algorithm thinking may play a more and more powerful role. Like if it's only like very simple game setting, maybe it's have a closed form in economics, then it's nothing about algorithm. But if it's a very complicated system and the many players are play in the system and have very different goal, then the traditional economics calculation may not work there, and the algorithm thinking may play a role. And all this complexity view, also this kind of approximate ratio point of view, which is very powerful. Like in Xiaotie may already mentioned that the applied of anarchy is really motivated by the idea about approximation algorithm in selective computer science, and also the efficiency of this dynamic of the equilibrium is also motivated by the complexity thinking in selective computer science. Also, as I already mentioned in the previous time, the interface between selective computer science and the industry or the applied science is also very interesting, because really both of us are trying to design algorithm to solve problem, but with very different perspective and have different approach, and this approach can be combined to do a much better job. So I will stop here.
Thank you, Pinyan, for the wonderful sharing. And the next question goes to Liwei. For those who don't know, Liwei and I are classmates in the same class in Shanghai University more than 20 years ago, and we have been good friends over all the 20 years. So therefore, I decided to ask you a very tough question. So you are the machine learning expert, and in your sharing you mentioned that deep learning has many kind of drawbacks, right? Then my question is, could you predict, for example, 5 years from now, what will be the situation? Will deep learning still dominate our area, or deep learning will encounter some bottleneck? And what is the possible theoretical breakthroughs that can make deep learning a second round of success? Yeah.
This is really a tough question. Okay. I think, let me think about the development of deep learning. What is the last biggest breakthrough in deep learning? In my view, it is transformer, a new architecture. Now, starting from NLP, but now applied in computer vision and all other applied areas. But transformer was developed more than 4 years ago. Okay, in deep learning and machine learning, 4 years is really a long time. Okay, so in the last 4 years, there's no big development breakthroughs in deep learning just after the transformer. So it means it's very difficult to make other breakthroughs in the same way as before. So we need some new approaches. So now I think in the past 2 years, there are two trends of researches in deep learning. One is applied to deep learning in other fields than the traditional computer vision, NLP, and speech. Now we apply deep learning to a broader areas such as natural sciences, like biology, like physics, like chemistry, and now Tian is also working on molecular dynamics and also drug discovery. So these are new applications of deep learning. I think that in the next few years, a lot of researchers will develop new machine learning models and algorithms in these new area applications. Why I think there should be new architectures? Because when you apply deep learning in something like physics, there are hard rules. There are hard rules governing, there are hard physical rules described by equations like PDE or ODE that describe the atoms, quantums of the relationship. Okay. So it's quite different from computer vision, NLP, and speech. For computer vision, NLP, and speech, there's no mathematical description of the data. Okay? You cannot simply write an equation of the data. If the signal is too complicated. But in physics, especially when you study atoms, it's totally different. There are very simple equations you can describe the physical laws. So you need something using mathematics to embed some constraint in the deep learning model. So I think might be a future direction. Another future direction is what I already talked about, is even for general machine learning models, when we need something more than just a test accuracy. For example, we need the adversarial robustness. Actually, I worked with Strong and Kun in the past few years on adversarial robustness. So our goal is to using a theoretical approach to tackle this problem. Because this problem, the adversarial robustness, is not just ask about test accuracy. We need something more. We need something that can describe in mathematics, in very rigorous mathematics. We need that the accuracy is not only for just test data points, but also in a neighborhood that precisely described in mathematics that the accuracy. So because we have such requirement, a mathematical requirement, I think we need to using theoretical tools to develop the models and algorithms. So that's right.
Thank you very much, Liwei. I cannot agree more. This is also why at MSRA we spend a lot of efforts on machine learning for science. I think that is truly a very promising direction. And next question goes to Wei Chen. And first of all, I want to congratulate you again on the ICM 10-year highest impact paper award.
Thank you.
And Wei, I know you have done a lot of theoretical research on, for example, distributed system, for example, online learning, social network, and all generated very impactful research. And I think this award is a kind of a reflection of that. And my question is, how do you view the connection between all these different areas, and what is the future of that? Yeah.
Thank you. So yes, it's true that my background is quite kind of from a diverse. I'm trained in theory. I was actually in Tsinghua University when I was an undergrad. I was the first theory class, so-called in computer science. And the first research topic we are looking into is cryptography. And then when I moved to Cornell, I studied distributed computing, theory of distributed computing, and got my PhD in that field. And did some work, also won an award there. And later in Microsoft Research, after some years, I started working on social networks, in particular influence maximization. So I have some diverse experience. So I just speak from my experience. It will not cover all the other people's experience. From my experience, I think as a theory researcher or basic science, basic researcher, we need to do things to more look up and look around to see what other areas are going on. And in theory researcher, it's sort of, from my observation, there's a tendency, theory researcher likes to go deep. Like if you have an algorithm has a n² running time, I'll improve it to n log n, and the other will come in to n log n or something. So it's going very deep. It's very tough, and I know there's a smart brains, even in our audience, can do this work very well. So, but this is only one side. Sometimes we also need to go broad to look around to see other areas, what's going on. And as Professor Ma Laoshi said, the current, a lot of things are changing. A lot of things are fusion with each other. Math and science and computing, they are fusing with each other. So there's a lot of changes. So as a theory researcher, we should not just look down, and we should look around more. I'll give 2 quick concrete examples. One is the famous RSA algorithm, by Rivas, Shamir, and Adelman is another example I think Ma Laoshi will like to give. These are, RSA is a beautiful algorithm, a small algorithm from number theory. But how they could develop this algorithm, and it's because in that age, people are still doing traditional cryptography. And the first thing, Diffie-Hellman proposed this new paradigm of public crypto. And that says because current traditional cryptography will not be enough for the online age, for the online e-commerce. And then RSA comes in and quickly invent this new simple algorithm. And this ever since becomes the driving force behind all the e-commerce. Every HTTPS request you click right now, underlying is running RSA. So its influence is huge. But this is because those great researchers, they are looking at the trend, the important things, not just improving their own algorithm. Another example from my own research experience, as I said, I did social network influence maximization. And the first influence maximization research and formulated as a optimization, discrete optimization problem is by David Kempe, John Kleinberg, and Eva Tadosh. Again, top researchers from Cornell, Kleinberg and Tadosh, and David Kempe was a student at that time. And they find in the data mining field good research in social networks, and they formulated in the theory as an optimization problem and use some modular maximization to apply to it and apply and get a very good result. And that paper becomes the most influential paper in the KDD, the data mining conference, and won the first Test of Time award in data mining. And actually it's also motivate me and my research colleagues to continue work on that, because we also see further opportunities to improve the algorithm, both for efficiency side and from the other applications to extend influence maximization into more areas and domains. So we work on online influence maximization, which also leads me to online learning. So all these are trends. And actually, just for influence maximization, they mostly publish in the applied field, but also it also attracts theory researchers like Christian Boggs and Jennifer Chase from our MSR New England lab. With their colleagues, they published a very nice breakthrough paper in SODA, a theory paper, to lead another leap in this algorithm development. And then other applied researchers in Sigmod and others come in to further improve the practical performance of algorithm. So this is an example. I see a good interaction between theory and applied people. Through this fusion, they work together and improve upon each other, so it has both impact in theory and in practice. So to conclude this, I just give one sentence as my suggestion is, in English, it would be avoid involution and embrace fusion. In Chinese, is 避免内卷。Because 内卷是避免内卷，拥抱融合。Because theory, you have a larger field. You don't have to 内卷 in your small algorithms and just work on more problems. There will be interesting more problems for you to explore. Thank you.
Thank you very much, Wei. I think what you share really means a lot to another Wei Chen, because I know you, Wei, you're from a math school and joined a computer science company working on machine learning and science. These are really diverse directions. And for all of them, there were some theories already. For example, theoretical computer science. For example, the OD or PD for natural science. For example, we have machine learning theory and also pure math theory. And when all of them putting together, when we think about the theory center of MSRA, are we just working on these existing theories, or there is a need to invent some new theory? And what if there is a new theory, what is the possible scope? We just want to hear some science fictions from you about a new theory.
Thank you, Tian, for giving me this opportunity that I can continue on my opening slides, I also mentioned some term like new machine learning theory. So you amplify it to new theory, right? So I think first of all, I can make some specific inputs, focusing the dynamics of learning and how to learn the dynamics. That is, yes, we do not know how does deep learning work, so we are leveraging variants of mathematical tools to do it, and we are working on the dynamics of deep learning. And I think this is just a starting point, and we think maybe the current math theory is not sufficient to do that. So we think that some theory for a composition like that may be very helpful to understand the neural networks. And yes, that is some of our personal source of the new math theory for deep learning. And the other direction is the new machine learning theory for science, maybe for, and even for math. So yes, we can collect data from dynamic systems, and maybe we do not know the underlying pattern. So we want to use the data to learn the unknown dynamics. But in some equations, we do not have very good understanding, like the 3D Navier-Stokes equations. And we also invite Professor Chen to give us the recent progress on that very important direction in math. So I think we need to work together for that, for how to use machine learning to solve the pure theory problems. So I think there are two directions, the new math, the new theory for machine learning, and we also need a new machine learning theory for the science problems. Okay.
Thank you. Thank you very much for the sharing.